time for section 8.6, which is all about radical equations and problem solving. Now, problem solving usually means word problems. You probably have caught on to that by now. That's their way of alerting us to some word problems. But in this section, we're only going to examine one type of word problem. So the section itself doesn't go all crazy with word problems. I think it's got like 2 different types, and we're just picking one type that's helpful and letting the other one go because it's just a little bit much. Okay, but the bulk of what we do will be talking about these radical equations. Excuse me, of course, my phone starts going off when I start doing this. If it's too intense, I'll pause the recording. Okay, sorry about that. That actually took longer than I thought. I guess I give myself credit for being a faster texter than I really am. So anyway, the bulk of what we're doing with these radical equations, and I'm just going to dive in. The book starts out with a rule, but the rule sounds like nonsense if you don't understand what they're referring to. So we're going to go to practice 1 and look at what we're dealing with here. Okay, so the directions have changed in this section. Anytime we're dealing with equations and we have an equal sign, the directions will talk about solving, not simplifying, for example. And so here we've got a little expression under a square root, and then here's what makes it an equation, that right there, and then 7. Okay. The way that we solve these radical equations, so equations with some kind of root in there, usually a square root, but not always, I'm going to come down underneath so that I don't tamper with the problem I copied off the pages of the book. If it's a square root, what we want to do is remember 2 things. First of all, with equations, what you do to one side of the equation, you immediately do to the other to keep it balanced. And then the second thing is what happens if you square a square root. Well, that's actually the same thing. We've seen this before, square roots. This is the same thing as that. And that might be what we look at more it's early, more often. Either way, just releases the insides. More significantly, because we're dealing with x's in algebra, this technically equals the square root of x unless we know x must be at least 0, and they've been telling us that a lot. Then we'd be allowed to say that either one of these quantities equals just plain x. And I think they're going to be doing that continuously for us. They don't like us in Algebra 2 to deal with absolute value bars too much. So basically, the method that we have to apply to both sides of this equation is to square away the square root and then balance that by squaring whatever happens to be sitting on the other side of the equation. Okay, now watch what happens here. This is the part where the book's rule comes into play. Thank you, Matthew. So now we have the inner expression released. Okay, and this is a brand new equation. It's kind of up a level is what I usually say. It's a new equation. Everything used to be trapped under a square root. So technically, even though that looks like an X, under a square root, it wasn't a whole true X. Now it is. So this is a new equation. It's been released from the trappings of the radicals and all that. Here's the problem, or the rule that the book puts down, and I'm restating it. The solutions, no, to this new equation are guaranteed. So we like things in algebra that are guaranteed because that's not always the case. To contain the solution or solutions that we're actually looking for. So what we're actually trying to solve here is still the one with the root in it. But the only way we could get at those solutions was to get rid of the root. So that now we can activate all these rules we know about solving equations. Now, contain. What this means is the new equation, because it, like I was saying, it's up a level, the x is not really the square root of x anymore, it's x itself. The new equation may have more solutions than the one that we're actually interested in. So what that means, when we know that that's the case, whatever solutions we get from solving the new equation, we're going to check in the original. And of course, they won't hit us with that right in the first example, but just to be aware of what's coming. Get your little golf club and try to poke it out. Okay, let me make sure this makes sense. So, got a new equation. It's going to have some solutions, maybe more solutions than we need. And so if we find any that don't fit in the original, we throw them out. So what I mean is, in terms of, we'll do a little so the solutions to the new equation are that circle, and then we'll just kind of come inside here. Smaller set. Okay, now sometimes we get super lucky and the following happens, and I think this will happen in the first few examples. The two sets will be identical. I don't know how to express a red circle on top of a black circle. I'm going to kind of do it with a dotted line. Sometimes same solutions, but that's not a guarantee, and we don't want to go into a problem assuming that that lucky situation will happen, even though it probably will early on. So in our problem, if I were to solve this out, so 3x minus 5 equals 49. If I add the 5 over, okay, so this is 8, 16, 24. So x equals 18, and I'm going to go ahead and immediately write, this is a possible or potential solution to the original. So we're going to check to see, so check. So we rewrite the original equation, whatever came off the pages of the book, and instead of 3 times x, we're going to have 3 times 18. And we want to know, does that come out equal to 7? So see if we get a true thing here. Let's see, 3 times 18 minus 5, does that equal 7? Like I did something wrong here. My horizontal multiplication, 8, 16, 24, 3, 4, 5, 4. Did I do one? Oh, because I can't count. That is 100% right. This is correct. That is a truth. The square root of 49 does equal 7, so the check comes out. My brain was just spazzing out. Okay, so that checks out. So that means x equals 18 is not only a possible solution, it is the solution. Or you could do this, like you'll see the book doing. Moving ahead to practice problem 2. Okay, word solve alerting us that we have to carry this thing down until we get x equals a number or more than one number. Okay, now, in order to be able to solve these radical equations, we have to get them in a certain format. And I'm going to say, in order to easily square both sides, because you could still get there carefully without doing what I'm about to say, but it would make it, trust me, so much harder. So here's the format that we need. Okay, go ahead. So we need the root on one side and then we need everything else. Okay, so in our problem, we've got the root. If we just leave it where it is and then add that 4x to the other side, then we're good to go. Then we're in the position where we can safely and easily square both sides. So I'm going to rewrite here just so that the squaring both sides does not interfere in the notes. Okay, so this is what it looks like. And my new equation, the one that I'll actually solve, I have the 3 minus 2x that got released from its root. And then over here on the right, I have to be careful to square the 4 and square the x. Okay. So 4 squared is 16, x squared is squared. And this is the new equation that I'm going to solve. Now, noticing that there's an x squared there, and then the left side has a x to the first and a no x, this looks very much like something that is going to be a trinomial that I need to factor. Let me subtract the 16x squared over here and kind of get things in a more familiar order. because typically for these type of factorings, the way we end up setting it up, everything on the left, 0 on the right. The 0 is what gives us permission to factor and then set those factors equal to 0. This is like a 6.8. All right, for this, I will have to pause. And I'll be right back. Okay, I'm very close to hitting stop recording there instead of resume. All right, now with something like this, I'm going to go ahead and do a little trick here because I absolutely despise things that are led by a negative. So I'm going to factor out a -1. That's the biggest and best GCF I can get my hands on. It changes the signs on everything else. And then I will attempt to end up with something like this, just in terms of formatting. Of course, I'm not there yet, but I just wanted to show you kind of where I'm headed. So the way that I'm going to do that, because it's not anything convenient here in terms of, you know, we just talked about the -1 was the only GCF I could get out. Let me take the 16 times the -3, and that's going to be a -48. Got something on my screen here, but a touch screen, if I touch it, stuff is going to go haywire. Careful, Matthew. Actually, that went pretty well. Okay, so I need the factors of -48 that add to be +2, and it's going to be -6 times 8, because -6 plus 8 would give us that +2. So I can leave the beginning and the end alone, just expand there in the middle. Okay. Now, in terms of factoring that out, I'm feeling maybe a 2x coming out there. Yeah, and then nothing comes out of 8x minus 3, but 1 itself. All right, so I've got now in solving these things, if we have a number sitting out front, we try just to be consistent to set every single factor equal to 0, but the number, that's not going to give us anything. There's no x there, so we can cross that out. Okay. Moving everything around, x is going to equal 3/8 and -1/2, maybe. These are our possible solutions. So we have to check both of them. And I should say check each one individually in our original equation. So I will check x equals 3/8 first, since that's the first thing we came up with. So instead of 3 minus 2x, I'm going to have 3 minus 2 times 3/8. And then minus 4 times 3/8 again, because I had 2 occurrences of the variable x in my original. Not quite, Matthew, I need a few more minutes. Now I want to see, does this come out equal to 0? Okay, so this is a little bit of a obnoxious check, and I don't have a calculator with me. I'm always so optimistic about, oh, this section won't need a calculator, and then I feel like it always does. All right, so 3, no, a few more minutes. I can cancel the 2 into the 8, come up with 3/4. I can cancel the 4 into the 8, come up with 3/2, and I'm curious, once again, no clue where this is going, whether all of that mess is going to equal 0. Okay, so this is like 3/1 minus 3/4. So I need to work on a common denominator. Fix by multiplying by what's missing. Okay. 12/4 minus 3/4 minus 3/2. Still no clue what's going on. 9/4. Now I think I see what's going on, but I want to put in enough in here so that the notes are helpful. Okay, so the square root of 9/4 is best approached by treating it as the square root of 9 over the square root of 4. And that gives us, lo and behold, 3/2 minus 3/2, which definitely equals 0. So we're good to go on that. So whatever we were testing here, I don't remember. So 3/8 is a solution. Now, we want to check the other one, which I think, test my memory here, was that negative 1/2? Yep. Okay. So, same idea as before, 3 minus 2 times negative 1/2 minus 4 times negative 1/2 is that going to indeed equal 0? Okay. So this becomes 3, the 2's are going to cancel. So I'll have 3 plus 1 here. Similarly, 2 can cancel into 4. Is that going to equal 0? Okay, so does 2 plus 2 equal 0? No. 4, and we can say very decisively, 4 does not equal 0. So x equals negative 1/2 is not a solution of our equation. It's only a solution of that upper level equation that we created by squaring both sides. So when we create our solution set, our answer is to box this in and then we get that if we want to adhere to the book's way of doing things. Okay, so good. I'm glad that the second example immediately got us into having to discard a solution. It's good not to get too far before you see that that can happen. Okay, the third practice problem here is going to involve a cube root, which also good that we're not getting too far into this before we temporarily leave square roots behind. Okay, so again, our goal is to have, in order to start solving this, is root on the left and everything else on the right. So what I need to have is cube root of x minus 2 equal to, I guess that's 2, before I start any serious hardcore solving. Now, squaring both sides is not the appropriate tactic here. This is a cube root. In order to release the inner expression from a cube root, in order to get rid of that root, I have to do the opposite type of power, or I guess you could say the matching power to whatever kind of root it is. So here's how I'm going to create my, my new equation. So the third power cancels out the cube root. Out comes the x minus 2. Then I've got an 8. Look at how easy this is going to be. All I get for a possible solution is x equals 10. Okay, that's all I get for a possible solution. So very quickly turn right around. This is the one and only time in this problem I'll have to do that. Put that 10 in there instead of my x. Oops. And I'm curious, if I plug it into the problem right off the pages of the textbook, will I indeed recapture my 3? Okay, so this is the cube root of 8 now, plus 1. Is that equal to 3? I hope so. Cube root of 8 is 2, plus 1. Okay, 3 equals 3. Yeah, we're good to go there. So that means we can keep x equals 10. Our one and only possible solution is actually a solution. I'm really curious if they're going to create a situation where we have no solutions. If they don't, I'll show you what will happen in that case. Oh, I didn't get it out, Matthew. Do you have yours by any chance? No. Okay, yeah, I don't have mine either right now. All right, diving right into the next practice problem. Back to square root, and they were kind enough to set this up so it's root on one side, everything else on the other already. But before we get too impressed by their kindness, let's consider what it's going to take to solve this. We square both sides. Okay. The left-hand side is easy as can be. So squaring away a square root. But consider that x minus 4 squared is really x minus 4 times x minus 4. It's that whole quantity squared. So we have to employ the distributive property a couple of times, or some people might call it FOILing. So x squared minus 4x minus 4x again plus 16. Let's clean that up. There's some like terms here that need to come together before we go too far into the rest of this. Okay. Now, I generally like, I'm headed towards trinomial factoring here. You can probably tell that I've got x squareds, x's, and regular numbers. Oh, wait, I'm not heading towards trinomial factoring. Notice that when I start collecting, and I always collect everything over on the left, which creates some negatives. Negative x squared, when I add the 8x over here, I'm going to get a 9x. When I subtract my 16s, they're gone. So I've got that. I want to put an alternative here, which I haven't done this very much because I wanted to create habits for us before we start seeing all the options that are out there. Let me subtract everything to the right. Again, putting the 0 on the right is my preference and mathematical tradition. The 0 could easily go on the left. So let me subtract, my 16s go away. Okay. Notice when you do that, your x squared comes out positive. And that's kind of nice because it's your lead term. Excuse me, get my hiccups here. If you don't like seeing that, you can rewrite if 2 equals x, then x equals 2, so you can write stuff either way. And go about the rest of the problem without having to mess with negatives. So my rule about consistently pull everything to the left, sometimes creates negatives, and you can avoid that if that bothers you. Okay, I'm going to stick with negative x squared plus 9x, since that's what I had gotten. And I'm being led by a negative here. I'm going to pull that negative out. I also have a GCF of x. I'm going to pull that out. Looks like I get this, which is exactly what I would get if I chose to approach it up there. Okay, so I want negative x to be equal to 0, or x minus 9 to be equal to 0. And I don't know why that came out looking funky. Oh, please don't do this thing and you completely break down. That's weird. It was back up like that. Who knows? Who knows why my eraser was not working? Okay. 0 without. Now, if I divide both sides by negative 1, x is going to equal 0. Good job. And then x is going to equal 9. Those are my possibles. So now comes just the grunt work, where you have to check, but I guarantee you checking is worth it. Okay, so this is, what are they? What are they, Matthew?
The first is, I think this question can make them two white.
Really?
No, they are.
What are they?
They're numbers.
Oh, they're numbers.
So 4, 5, 1, 8, 3, 9.
Okay, when we take the square root of a number, we always have to get a positive. If we wanted to express the fact that negative 4 also can square back to being 16, we would have to call it, there's the negative square root and the main square root. So unfortunately, even though this feels like it should come out, eraser is still not working. It's so bizarre. Technology.
What's the first step?
So x equals 0 is not a solution. Now, let's check the other one. X equals 9. I feel like I'm going to start writing faster out of fear that the whole program is going to implode on me. Okay, so 16 plus 9 is 25 under the root. This looks more promising. Yeah, I'll just take it all the way down. So x equals 9 is our solution. That's what we get to keep.
Equals 9.
Oh, I do see some lines on your screen there.
This is a 7. I got a 7.
Good job. Oh, goodness. I see where they're heading and I don't like it. I'm going to insert something here. What if none of the possible solutions check out?
Oh, a bird in our window.
I think that might have been a leaf. I hope it wasn't a bird.
It was a bird.
I don't know if you guys can hear the conversation that's going on here. And this should be familiar. Then what we get is no solution, like we've gotten several times throughout this class. Or the equivalent, like, shortcut way of writing that would be method.
I'm doing class like you are.
You are totally doing a class like I am. It doesn't look like they're leading us to that, but just so you know.
That is what it said, push that button, and that button, that button. That's why you do it.
Now this one, I'm slightly torn on whether it's productive to do this, but I think it is. It's it's tough, but kind of need to see it. It's sort of like the logical conclusion of what we're talking about. Now, all of a sudden, I've been telling you, put the root on one side, put everything else on the other. Well, what happens if you have two roots? Two roots, because in that case, we can't have what is typically our goal, root on one side and everything, literally everything else, on the other. So, but what we can do is just separate the roots. And that makes things slightly easier. Again, this is all about ease and convenience. It's not about right or wrong. You could solve the problem with both roots on one side. It would just make your squaring both sides phenomenally worse.
Push that button.
Okay.
Make it away.
Good.
I pushed it now. Make it on the back.
So for example, 2 minus, and it's usually best to have the root being subtracted behind the number, not the other way around. All right, now, if I go right into the squaring both sides, this is going to take some caution. Left side, just a real easy thing, again, like usual. But the right side, got to be really careful. This is telling us that we have matching little subtraction problems being multiplied via FOILing. Okay, so for example, we've got 2 times 2, and then we've got 2 times the negative square root of 3x. So the way we would organize that is the negative sign would go first, then the 2, and the root. All right, same multiplication repeated. A negative square root of 3x times a 2, so the negative goes first, then the 2, then the square root part, and then finally we have a negative square root of 3x times itself, essentially. Negative times a negative yields a positive. Square root times a square root just releases that inner expression. Okay, now, as I clean this up a little bit, notice that in a way it feels like we haven't gotten where we need to be because we still have a root. And we're used to squaring both parts and like being done with the roots. A good rule of thumb is however many roots you start the problem with, that's how many times you're going to have to square both sides. I'm going to now rearrange this. I want my root on the left. So let's see, rearrange.
Push that button right there. Wait.
Let's erase. Okay, so we're going to go through this all again. I feel like I would like, I don't know if you need to be, remember when you fell off the chair yesterday because you were sitting on it the whole way? Yeah, your whole little self there needs to be on the chair. I'm going to add the 4 root 3x over to the left. Now notice what I have here. I'm not jumping too many steps. I'm just leaving everything else as is. Just the square root of 4 times the, or 4 times the square root of 3x just crossed over. Okay, now I'll bring everything else over there. So I will be left with 4 times the square root of 3x equals 3 when that 1 becomes negative and combines with the 4. And then my 8x will become negative, combined with the 3x. Okay, then we square both sides again. This is so unfortunate. You can see why I was thinking about avoiding this problem, but it's good to know what to do. All right, so very carefully, when I square the 4, I get a 16, and when I square the square root, out comes that inner expression. And then being super careful here to square the subtraction problem correctly using FOIL. All right, 16 times 3, what is that? 48, the x. Then I've got 3 times 3 is 9. 3 times negative 5x, negative 15x. Negative 5x times 3, negative 15x again. And then the negative 5x's, when multiplied to each other, will turn positive 25x squared. Okay, now here's one of those times, look at all of the terms I have on the right. Even when I bring together the like terms, there's still a lot more going on the right than there is the left. Let me do one more thing. Let me rearrange the right side. I would like to see that 25x squared as my lead term first, then followed by minus 30x, then followed by plus 9. That's the way I want it to be. Okay, so if I subtract 48x over, what is that, 48, 58, 60, 78. Oh, you've got to be kidding me. And then I can rewrite. And of course, theirs comes out all nice. So I'm wondering if I did something wrong. So, you know, worst case scenario, if I did something wrong, you guys will get to see me erase a bunch, although my eraser doesn't work. Fun times. No GCF. I just want to make sure, like, backtrack here. Make sure everything went fine for. Not yet, almost. Okay, and that was 4. Okay, that was good. This came over. Okay. 3. That's good. Okay.
Making a map. Making a map.
All righty, well, let's go for it. The AC method here, 25 times 9. Hey, you're hanging off the chair again. Remember, I don't want you to get hurt. Our chairs are deceptively dangerous. Okay, and I don't remember what that is. I know, yeah, I'm going to be really cautious here, even though I feel like I could figure that out easier. 225. I need to factor 225 with 2 negatives.
Can you push that button?
Just out of curiosity, what is 75 times 3?
Push this one. I'm going to calculate.
Okay, I did. Oh, perfect. perfect, negative 75 times negative 3. I'm like, 78 is just such a suspicious number when we're dealing with 25s and multiples of 25s, because I know 75 is a multiple of 25, so it's probably likely to feature in this problem. Okay, so I can go minus 75x minus 3x plus 9. I was getting all scared for nothing, right? Out comes a 25x. That's an x minus 3. Next two terms are led by a negative, so that better come out with the GCF. All right, well, thank God this is wrapping up rather nicely. Of course, I've still got all kinds of checking to do, but at least I'm getting two pretty clean looking answers. One's going to be a whole number, one's going to be a fraction. We take what we can get. X equals 3 and x equals 3/25. There's that. So these are our possibles. Again, it's easy to get carried away when we get to the end of a ridiculous amount of algebra. And think, oh, those are our answers. Let's box them in and move on with our lives. But back to the very beginning of that problem, which I have to look up. It's been so long ago. Square roots were both on one side of the equal sign. That's okay. Okay, and we want to know, does all of this collapse down nicely to be just a 2? Wouldn't that be great? Okay, 8 times 3 is 24, plus 1 is 25. 3 times 3 is 9. Does it equal 2? Let's see. 5 plus 3 does not equal 2. 5 plus 3 is 8. So we know we're going to throw out our pretty whole number and attempt the 3/25.
I think it's a pretty whole number.
Because my pretty whole number didn't solve the problem. Okay, so let's try the ugly fraction. Oh man. Once again, I'm getting scared. This is going to be the messiest thing ever. Oh well. If it comes out giving us a solution, I'll forgive it. All right. Okay, so is that going to be a 2? Okay, so we've got 24/25 plus 1 under the first square root. We've got 9/25 under the second square root. Does all of that collapse to 2? Now I know I can call this 1. My eraser's not going to let me do it. That just boggles my mind why everything else appears to be working except the eraser. So I'm going to have to rewrite so I can go 25/25. Yay for that. Let me go ahead. If I simplify this down, this is going to be 3/5. That'll save me a little bit of writing of roots. Okay, so 49/25. Does all of this equal 2? Simplify it down, I get 7/5 plus 3/5. I'm feeling positive about this. This is looking good. 10/5. It does equal 2. Okay, so x equals 3/25. So that's sort of a worst case scenario when you have 2 roots. And yes, in case you're wondering how bad can these things get, and in future classes, they do absolutely give you more than 2 roots per problem, but not in this one, from what I'm seeing. All right, so we've got one more problem, and it is our word problem, our lone word problem. I had talked a little bit about the Pythagorean theorem in a previous recording. Can you go find some clothes for me, Matthew? So maybe this will look a little bit familiar. If you have a right triangle, so right triangles are triangles in which there is one right angle. There can never be more than one right angle for reasons of geometry. And right triangles can look any number of ways. I've drawn the one that the book uses representatively. Drawing a weird one down here. Those can be right triangles as well. The important thing about a right triangle is directly across, okay, see how cold it is? Directly across from that right angle is a side called the hypotenuse. It's always the longest side in the right triangle. And that is related to the fact that the 90-degree angle is always the biggest angle. So let me just, oh yeah, it probably will help. And we call the hypotenuse C because we're always talking in terms of A, B, and C with the Pythagorean theorem. Now, in terms of the other two sides are the legs. So just since I drew 3 triangles, we're going to keep this up. And the legs are named A and B. It really doesn't matter who's A and who's B. Absolutely does not matter. A, B. So you just kind of slap that on there. The relationship, the only thing that matters is that C ends up squared all by itself on one side. So A squared plus B squared equals C squared. That is the Pythagorean theorem. Okay. When you square each leg and then add it to the other leg squared, the result will be the hypotenuse squared. Okay, now the way we use this and the way this relates to square roots will come out in this very simple practice problem. And I'm just gonna, I think they say find the unknown leg, but they call it A, so I'm gonna find A here. So here's our right triangle, 6 meters. Notice this is a true word problem, units and all. So I have to be careful that my answer is in terms of meters. Okay, so this is going to be C. So if I know that A squared plus B squared equals C squared, well, A is what I'm looking for, so I'm going to keep calling it A. This other leg has got to end up as B, like that. All right, A squared plus 36 equals 144. Let's see. Oh, my head just exploded. I think that's 108. I really, I'm not feeling it this morning. I want to be extra cautious. 8 plus 6 is 14. Yeah, there is that 0. Okay, so what is going to happen is I am going to square root both sides. This is like going the other way from what we've been doing. Square root, square root. Now, remember that the square root of A squared is technically this. Now, I'm doing this in a bit different of a way than the book. You can just kind of memorize what the book does and you'll be good to go. This is a word problem. We know, they didn't tell us any other information, but we know that A, B, and C technically have to be positive numbers. So I know I keep harping on that sort of seemingly obscure algebraic rule. We can say this. Now, technically again, in a pure algebra problem with no restrictions, we'd have to worry about positives and negatives, but we don't have to do that here. These are triangles. Triangles have, positive sides. Okay, now this could be my answer, or it could not be my answer. I have to think about, what about those perfect squares? Be done in a minute. So 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Let's see. 9 goes in there pretty nicely. Oh, but it's not big enough because this, here's what, I'll just walk you through this. If you pick a square root, a perfect square that's not big enough, so 12 is 4 times 3. Lo and behold, I have more perfect squares in there. So technically 9 times 4 is 36. I stopped my list at 25. I should have gone 36 fits in there. The good news for me is that I can still get the right answer as long as I'm careful to recognize that there was still a perfect square hiding inside of my 12. Okay, 3 times 2. So the answer is 6 square root of 3 meters. And they don't take this out, plug it in their calculator, find the approximation. So I'm not going to either. Now, if you would like, you are welcome to look at example 7 and try to apply the Pythagorean theorem in a deeper word problem context. I'm going to stop right there, though. I just wanted to, in the middle of everything else we were doing, just kind of expose you to the Pythagorean theorem. So, and notice the method solving that. It's a little odd that they throw it at the end of this section. We didn't actually do what we had been doing the whole rest of 8.6. We did not square both sides. In other words, raise them up to the higher level. We brought them down to a lower level. We square rooted both sides. So I can think of better places maybe to put that, but we'll go with it. They wanted us to teach it there, so we went ahead and did that. Okay, let me wrap up this recording and get it on YouTube.